Okay, folks. So, as we left off, we did Chapter 5 homework. Now we're going to look at some Chapter 6 homework, which I only assigned 3 problems for, so this shouldn't be too long. We worked on problems 1, 4, and 10. So let's look at 1, 4, and 10, respectively. So problem 1. Which of the two cloud droplets or rain droplets would you expect to have more scavenging gas and more effective in scavenging gases from the atmosphere? And so explain your reasoning. This is kind of open-ended, but there is a somewhat doable answer here. Cloud versus rain droplets. So the first thing is to consider the size of the droplets, consider residence time, consider surface area and total number of droplets that would be present in these situations. So when we're looking at droplets, cloud droplets are usually between 5 and 50 micrometers, while the rain droplets are raindrops are between 900 micrometers to 5 millimeters. So, cloud droplets, the sheer number, we have more surface area. More surface area in these smaller droplets. And so because of that, you can have more absorption. And then more drops are going to be present in the cloud than as opposed to the raindrops. And so they're going to be better able to scavenge molecules. However, but because of their lighter and smaller, they will also have longer residence time. So if you're talking about an overall binding, you have more time for more things to bind, but if you have a continuous more rain, you can wash things out, but it might not be fully saturated at that point. So with that in mind, cloud droplets will definitely be able to absorb molecules better, but they might take longer to remove them from the atmosphere. So take that what you will. Now problem 4. Problem 4 is to consider fly ash. Fly ash with a density of 1.8 grams per mil is an aerosol containing particles averaging a diameter of 13 micrometers and with a concentration of close to 800 micrograms per meter cubed. Using the average diameter to calculate the settling velocity and settling rate of particles in still air. So there's a few other things we need to assume. One is the eta of 1.9 times 10 to the negative second grams per ms, grams per meter seconds, and the density of air as 1.2 times 10 to the third grams per meter cubed, and the C of 1016, where we're going to make the assumption that 13 micrometers is close enough to 10 micrometers to find that C value. So we need to make some conversions to get things into the units of grams or meters or meter cubed. But our velocity, or settling velocity, is simply this equation. P minus PA times my C times my gravity times my D squared all over 18 eta. So this will find my first value, my settling velocity. So to do this, first things first, we need to convert grams per milliliter density into grams per meter cubed. So 1.8 gram per milliliter, there is 1,000 milliliters in 1 liter. I do believe there's 1,000 liters in a meter cubed. So basically that puts me at 1.8 times 10 to the 6th grams per meter cubed as my density. Now C is already in the correct units. Gravity is 9.8 meters per second squared, and I need to turn my diameter from 13 micrometers into meters. So times there is 10 to the 6th micrometers in 1 meter. So that puts us at 1.3 times 10 to the negative 5th meters as my diameter. So let's do this now. So 1.8 we'll turn this 1800 minus 1.2 times 10 to the 3rd grams per meter cubed times my C 1.016 times gravity 9.81 grams per meter squared times 1.3 times 10 to the negative 5th squared over 18 times 1.9 10 to the negative 2nd. So this should get me in units of, so let's see, if this is grams per meter cubed, C is unitless, this is meters per second squared, this would be meters squared, and this is units of grams per meter second. So seconds, meters, grams, meter squared, actually, sorry. So I'm left with meters per second as my unit. Meters per second. So let's plug that in. 1800 minus 1.2. And then I times by 10 to the 3rd. Times by 1016. Times 9.81. Times, in parentheses, 1.3. Times 10 to the negative 5th squared divided by 18 divided by 1.9 10 to the negative 2nd. All that is small number. So that's in meters. That's in meters per second. So I'm going to convert this into centimeters to make this a little bit more reasonable. So when I times by 100 to convert this into centimeters, we have the settles at a velocity of 0.88, we'll say 6 centimeters per second. 0.886 centimeters a second. So not even a full centimeter every second. Now the second part of this asked us for the settling rate in units of grams per meter squared second. So to do this, we need to utilize our velocity, which we just got, and our concentration in grams per meter squared. So let's turn this back into meters per second. So 8.859 times 10 to the negative third meters per second, and we're multiplying that by my concentration, which was 800 micrograms per meter cubed. Now I obviously need to turn micrograms into grams. So there is 1,000 micrograms, or 10 to the 6 micrograms in 1 gram. That's going to get that. Meters going to cancel meters, and we'll be left with grams per meter squared second. So take our number. I'm multiplying this by 800, but then I'm dividing by 10 to the 6th. And we have a settling rate of something like 7.088 times 10 to the negative 6th grams per meter squared second. So that's how many particles and particle weight settles in a meter squared area every second. Very small number, but something we can do. It's a ugly equation. It's an ugly equation, but once you learn how to use it, it's really quite simple. Problem 10. A sample of solid aerosol is collected from a rural area and found to have a composition of aluminum of 2,400 milligrams per 2,400 milligrams per kilogram, and lead of 3.4 milligrams per kilogram. Using data from the crustal abundance of elements, Appendix B1, calculate the chemical concentration factor for lead. What might be the reason for such a value such as you have obtained? So we need to look up the soil concentrations for these guys. So the crustal abundance concentration for these guys is something like 81,300 milligrams per kilogram of aluminum versus 14 milligrams per kilogram of lead. So my equation is really just, so the concentration of lead over aluminum as in the air divided by the concentration of lead over aluminum in the ground. And that would give my concentration factor. So really, 3.4 divided by 2,400 on the top part, but 14 over 81,300 on the bottom part. And so that will give us clearly, well, there's far more lead in the air than you would expect by its natural abundance in the crust. So the top part is 1.4, we'll say 2 times 10 to the negative third, and the bottom part, 300, something like 1.72 times 10 to the negative fourth. So with that in mind, this divided by this, we have a concentration factor of 8.23 times more concentrated. And the obviously, even though this is a rural area, this dust could be coming from urban environments. This is actually could be coming from traces from leftover from leaded gasoline. Leaded gasoline is an ongoing and pervasive problem that produced a large amount of lead that kind of coated the surface of many environments where lead would not normally be found. And so that's probably the most likely reason why it's 8.22 or 8.23 times more concentrated than we would expect. Okay, now, as I said, those were the 3 problems I had assigned, so not too bad. But that's how you use the equations of this chapter. See ya.